Okay, so again, now we're looking at the speed of sound this time, and interestingly, the speed of a sound wave in a fluid depends on the fluid's compressibility and density. And you can see the velocity here is directly proportional to what's called the bulk modulus, and it's inversely proportional to the density. Okay, now what that means is that as the bulk modulus increases, so too will the velocity. That's what a direct proportionality means. As B increases, so too will V. The density is under the line, which means it's inversely proportional, meaning to say that if the density increases, then the velocity will reduce. Okay, so that's what we're talking about. So basically, a low density fluid will have a higher velocity, and that's the idea there. Also notice down here, it might be a little bit unclear, but it says that bulk modulus is equal to the change in pressure over the ratio of the change in volume to the original volume. Okay, so what that means is that the bulk modulus itself is directly proportional to pressure. So therefore, the higher the pressure, the higher the bulk modulus, which means that the higher the pressure, the higher the velocity. Okay, so higher pressure, higher velocity. That's what that means there. Okay, and also you can see that the bulk modulus is inversely proportional to the change in volume over the original volume, that ratio. So what that means then is that the bigger the change in volume, okay, so the more compressible the liquid is, the bigger the change in the volume, the smaller is the bulk modulus. Okay, so a large denominator means that this number will get smaller. They're inversely proportional. Okay, and if the volume changes a lot and the bulk modulus decreases, so too will the velocity decrease, because the velocity is proportional to the bulk modulus. Okay, so this is just a little Okay, then look, the speed of sound in air is also dependent on the temperature of the medium, or the air in this case. So for instance, the velocity is equal to 331 meters per second multiplied by the actual temperature of the medium divided by 273 to the power of a half there, you see. Temperature is measured in Kelvin, as you see, and 0 degrees is 273. So depending on your temperature, you're going to be plus 273 or you're going to be minus 273. You're going to be less than 273, depending on what your temperature is. And what you do is you multiply, the brackets means multiply, so you multiply by the 331 meters per second, and that will give you the velocity of sound in your medium. Okay, so for instance, look, in air at 0 degrees we have 331 meters per second, but air at 20 degrees is 343 meters per second. So ask yourself then, is the velocity of sound proportional or inversely proportional to the temperature? Well, 331 at 0 degrees, it rises to 343 at 20 degrees. That means as this increases, as the temperature increases, so too does the velocity, and that's what's called directly proportional. Okay, here's the speed of sound problem then. An explosion occurs 275 meters up in the sky, I guess, above an 867 meter thick ice sheet that lies over seawater. If the air temperature is minus 7 Celsius, not Kelvin now, it's minus 7 Celsius, how long does it take? Now, how long means how much time, so we need to work out time. Does it take the sound to reach a research submarine 1,250 meters below the ice? Given that the bulk modulus of ice is 9.2 by 10 to the 9 pascals, the density of ice, that's rho ice, density of ice is 917 kilograms per meter cubed, and the velocity in water for sound is 1533 meters per second. Okay, so the overarching thing anyways, we have to work out time. How long does it take the sound from the sky to reach the submarine submerged? Okay, so the first thing we do is we have speed of sound and then time traveling in the air. Okay, so the speed of sound is 331 meters per second multiplied by the temperature over 273 to the power of a half. Now the second line is a repeat, except that we have 266 to replace the temperature. Now 266 comes from minus 7 up here. Taking 7 from 273, you get the number 266. It's as simple as that. We have got to convert to Kelvin right there. Divided by 273 to continue, and to the power of a half. Multiply it out, you get the velocity of sound through air is at that temperature of minus 7 Celsius, and in Kelvin 266 is 327 meters per second. That is the velocity of the sound in air. Okay, that's great, but the question said how long, which means we have to work out time. Okay, we do have velocity at that temperature, but we've got to continue on then. We've got velocity is equal to distance divided by time, and it's time that we actually want to work out. So we bring time to the lefty and switch all the other variables to the righty, which means we end up with distance over velocity. In air, it's 275 meters up in the sky, so that's in air. 275 meters divided by the velocity, which we just worked over on the lefty here, is 327. So do a divvy, and we get an answer. Temperature, time in air, I mean to say, time in air is 0.841 seconds, and that's just simple calculator plug and chug. Okay, so the sound has gone through the air, now it's got to go through the ice. Okay, so this time we've got a solid, we're talking about ice, it is a solid. Velocity is equal to this formula we saw earlier on, bulk modulus divided by the density, rho is the density, to the power of a half. So we have values for the bulk modulus of the ice, 9.2 by 10 to the 9. We've got the density of ice given from above there, right there, 917. Do the division, put it to the power of a half on your calculator, or 0.5, and therefore we have the velocity in ice is equal to 3.2 by 10 to the 3 meters per second. Yet again, it's not the velocity that we actually need to find, it's part of the way, it's on the path, but what we've got to find out is we have to find the time that it's in ice. Okay, so we use the formula again, velocity is equal to distance over time. Look at your speedometer of your car, your motorbike, and you see that on your speedometer it's measured in kilometers per second. That's distance over time. Okay, so velocity is distance over time, straightforward. We need time, and so we do a switch. The time switch is left, and we switch everything else to the righty, so we end up with S over V, distance over time, which is 867. That's the distance or the depth of the ice, an 867 meter thick ice sheet, and we've got to divide by the velocity, which we just worked over in the lefty here, and we plug and chug again. We get the time in ice, the sound. The amount of time that the sound passes through the ice takes 0.271 seconds, pretty quick. Finally, the sound wave's got to make its way underneath the water then to the submarine, which is a distance underneath the water, under the ice and under the air, and so the time in water comes from, okay, velocity is distance over time, time is distance over velocity, and the distance is 1250 meters under the water, and the velocity of sound in water is 1533 meters per second. Plug and chug again, and we get a number 0.815 seconds, and the total time then is the time in air plus the time in ice plus the time in water. Do an addition, small little number, 1.93 seconds, and that's all it takes for the sound wave, the sonar if you like, to make its way down to the submarine. Okay, intensity of sound waves then, I'm going straight to this direct formula here. Intensity is equal to the power divided by the area. Now this is easy to imagine if you have ever used, now again I'm switching to the analogy of light waves, and for instance if you have a magnifying glass and you focus the rays of the sun onto a piece of paper, you know that if you focus it onto a small pinpoint area, the smaller the area, the more intense will be the light, and you'll cause the paper to burn. That's the idea there. So the smaller the pinpoint area that you focus it on, the bigger the intensity. Also, The bigger the power, okay, so if it's a cloudy day, you've got less power from the sun's rays. If it's a crystal clear day, blue skies and all that good stuff, you've got lots of power, and therefore you're also going to increase your intensity. So look at it, it's a direct proportionality. Intensity is directly proportional to power. Intensity is inversely proportional to the area, and straightforward as that.